Now I'm going to talk about calculating the electric potential and what that means. So just the same way that there's a relationship between the force on a particle and the electric field vector. So you know that the force on a charged particle is equal to the electric field vector times the charge of that particle. We also have a relationship between potential energy and electric potential. So the potential energy, U, is equal to the electric potential times the charge of the particle. So, notice that those two formulas look exactly the same. The thing that we've already discussed, the electric field vector, is related to force in that way. And the thing that we're discussing now, the electric potential, is related to potential energy in that way. The SI units for the electric potential are joules per coulomb, but we give that its own name. That's volts, and that's something that's going to be a very big deal as we talk about electricity. And so if you want a way to kind of visualize, imagine what the electric potential is, you can always think of the electric potential as the potential energy of a 1 coulomb, a positive 1 coulomb charge at that location. Okay. And remember that, there are some questions that I'm going to ask about work also. So keep in mind as you do these that work done by a conservative force is equal to negative change in potential energy. So if you have a way to calculate the electric potential, then you multiply that by the charge of your particle to get the potential energy, and then you use this relationship to find the work. There are two ways that we're going to calculate the electric potential. The first one is for individual fixed charges. And that formula is that the electric potential is equal to 8.99 times 10 to the 9th times the fixed charge divided by R. This looks a lot like the formula for the electric field vector magnitude due to a fixed charge. The differences are this Q now isn't an absolute value. So if you have a negative fixed charge, you put that negative into this expression. And the other change is just notice that R is, linear. It's not squared. Okay. The second relationship, so this is what you'll use if you're given one or more individual fixed charges. This is what you'll use to calculate the electric potential. If instead of being given individual particles, you're given a function. So if you're given the electric field vector as a function of x, or it could be y or it could be z, but if you're given a function of one component of a position, then the electric field value is equal to negative dV dx. And so if you rearrange this, what that says is that the change in electric potential is equal to the negative integral, and this is a definite integral from point 1 to point 2 of E dx. Okay, so what we're calculating here is the change in electric potential of an object in going from point 1 to point 2. And I'll do examples of both of these. But so what you have to remember is there's only two ways to calculate electric potential. There's one way if you have fixed charges, and there's another way if you have E as a function of X or Y. Okay, so for the first example, let's do it in the case of fixed charges. So let's say that we have a fixed charge, a positive fixed charge there, a negative fixed charge with the same magnitude there, and we want to calculate the electric potential at that point P. Given that this distance is 1 centimeter and this distance is 2 centimeters. And let's say that Q is 3 times 10 to the minus 10th coulombs. And what we want to calculate is first, calculate the electric potential at that point P. And then second, what's the potential energy for a proton at P. We did something similar to this in calculating the electric field vector at a point P. We're going to calculate the electric potential due to the positive Q charge. Then we're going to calculate the electric potential due to the negative Q charge, and then we're just going to add them up to get the total electric potential. So the electric potential due to this first charge, let's see, what am I going to call this? I'll call this due to the positive Q charge, is equal to 8.99 times 10 to the 9th times the charge. It's not absolute value in this case, but that is a positive charge. So 3 times 10 to the minus 10, and then divided by the distance. And this time, remember, you don't square it. And we get an electric potential due to the positive charge of 269.7 volts. Man, look at how much simpler that was because we didn't have to deal with vector components and stuff like that. And you can see why it's simpler to deal with electric potentials and voltages than with those electric field vectors. Although those electric field vectors are going to be really important when we start talking about magnetism. Now we have to do it for the negative Q charge. So the electric potential due to the negative Q charge is 8.99 times 10 to the 9th times the charge here. Again, just trying to clarify that when you're doing the electric potential, you put the actual signed values in here. So this time it's negative 3 times 10 to the minus 10. That's different than the electric field vectors where you just use the absolute value. And we're dividing this by R. We have to figure out what that R is. So here's what we have. We know that this leg is 0.01. This leg is 0.02. You can use, well, if you knew that angle, if you figured out that angle, you could use SOHCAHTOA. But the easiest way to do this is just the Pythagorean theorem. So 0.01 squared plus 0.02 squared square root. And so I'm going to replace this with 0.01 squared plus 0.02 squared all square root. And we get a value of negative 120.61 volts. And so the total electric potential at that point is 269.7 minus 120.61, and that is 149.09 volts. Okay. By the way, this has units of volts, but this is not a voltage because it's not a difference between electric potentials. This is just an electric potential at one single spot. Okay. If we calculated the electric potential at two different spots and then subtracted them, that would be a voltage between those two locations. Okay, so now that we have the electric potential at that point, we want to figure out the potential energy for a proton that's at that point. So this is A. And now for part B, we're just going to use the fact that the potential energy is equal to the electric potential times the charge of the particle. So this is going to be 149.09 times the charge of a proton, which is 1.602 times 10 to the minus 19. And you get, come back, 2.39 times 10 to the minus 17 joules. So you can see it's pretty simple if you're calculating electric potentials due to fixed charges. Now I'm going to do an example where we have a function for the electric field. And so in this case, let's say we have parallel charged plates. And they cause, like parallel plates always do, a constant electric field. Of 5.0 times 10 to the 5th newtons per coulomb. And now we're going to say that we're going to look at 2 points inside this electric field. The point P1 is at 1 meter, and the point P2 is at 1.10 meter. And first, we're going to calculate the electric potential difference in going from point 1 to point 2, which is another way of saying V2, the destination, minus V at the start. This should be 1. And first we'll do it if the plates are arranged this way. And then for this potential difference, we'll calculate the potential energy difference for an electron moving from that point 1 to that point 2. And then we'll calculate the work done to the electron by the electric field as it goes from P1 to P2. And then the last thing I'll do is just show you what would happen what if these were oriented in the other way. So we want to calculate V2 minus V1 if we had the negative plate on the left and the positive plate on the right. Okay, so first we're assuming that we have the positive plate on the left and the negative plate on the right. And the effect of that is that at every point between these two plates, the electric field vector is pointing towards the right because it always goes from the positive toward the negative. And so the way that comes into this problem is that our electric field vector, we're only doing this as a 1D problem, so we don't have to worry about components. Everything's just happening along X. But this is, what did I say that value was? So 5 times 10 to the 5th, and it's moving in the positive X direction. So E is positive 5 times 10 to the 5 newtons per coulomb. And now to calculate the potential difference, we're just going to use the definite integral from the P1, which I said is 1 meter, to P2, which is 1.1 meters. So those are the bounds of the integration, 1 to 1.1. The E is 5 times 10 to the 5th, and we're integrating with respect to X. And I forgot to put in this negative. That's important. That's part of the formula. Okay, so let's do this integration. Notice that in your boundaries of the integral, the one on the bottom is always your starting point, and the one on the top of the integral is always your ending point. So we have, if we integrate this, we have 5.0 times 10 to the 5th times x, and we still have that negative sign, and we're evaluating this from 1 to 1.1. So this comes out to be negative 5 times 10 to the 5th times 1.1 minus 1. And so we get negative 5.0 times 10 to the 4th. And this is in volts. So what we've actually done is calculated the voltage between these 2 points. And if we switched the order of those 2 points, if we were going from the other one, the second one, to the first one instead, it would switch the sign of this calculation. Okay, the second thing we want to figure out is, now we have the electric potential. What's the potential energy for an electron that's making this path from point 1 to point 2? And that's pretty easy. The change in potential energy is the change in electric potential times the charge of the particle. The particle we're talking about is an electron. So this is negative 5 times 10 to the 4th. The charge is negative 1.602 times 10 to the minus 19. And so we get a potential energy change of 8.01 times 10 to the minus 23rd joules. Okay, does that make sense? Well, think about what happens in a gravitational field when you move an object against the gravitational field. Okay. So moving an object with mass against the gravitational force means lifting it up into the air. And our formula for potential energy said that as you lift an object higher into the air, the potential energy increases. We're essentially doing the same thing here with this electron. We're making it move closer to the negative plate and farther from the positive plate. So we're fighting against the force of this field to move the electron. And so what we would expect is for the potential energy to increase. And you can see that that's what it does. Now to figure out the work that's done by this electric field during that motion of the electron, all it is using the formula that work is equal to the negative change in potential energy. And so the work done on this electron to move it over this path that we've defined is just negative 8.01 times 10 to the negative 23rd joules. So in moving this particle along this path, are we adding energy to the electron or taking energy away? Remember, positive work means adding energy. Negative work means taking energy away. And so in fighting against this electric field, we are taking energy away from this electron. Okay, the last thing I wanted to do was just show you how this calculation would change if we had the plates oriented the other way. So this time, let's say that our plates, we have our positive over here and our negative over here. the electric field vectors always point from the positive towards the negative, so our electric field vectors will be like this, okay? And that means that for our one-dimensional vector field, those are going in the negative x direction, so our E is negative 5 times 10 to the 5th. And this is newtons per coulomb. Okay, so that's our function. Since it's constant, you know, it doesn't show x, but at every x, this is our electric field. So that's a function. You know, you can think of this as E of x. And so our change in electric potential is negative integral from the starting point to the ending point of negative 5.0 times 10 to the 5th dx. And so the two negatives here cancel. We get 5.0 times 10 to the 5th, evaluated from 1 to 1.1. And that gives you 5.0. Whoops, I didn't put the x in here. You get that x from integrating. So 5.0 times 10 to the 5th. And then times 1.1 minus 1 is just 0.1. And so you get positive 5.0 times 10 to the 4th volts. And so since we turned these plates around, we got a negative answer for the voltage. Okay, and then if you went through the other things with the electron moving through this new electric field, this electric field oriented the other direction, you would get all the same magnitudes but opposite signs for all of these answers.